Thanks for coming to the temporal graph reading group today, everyone. We have Giovanni here, who will be presenting graph-based virtual sensing from sparse and partial multivariate observations. And Giovanni, the Felice, is a PhD student in the data mining and machine learning group at the University of Liverpool, and a visiting scholar at Università della Svizzera Italiana. And his research, sorry for the Italian pronunciation.
No, it's wonderful.
His research focuses on time series and spatial temporal analysis, with a particular focus on material weathering and performance prediction. And previously, he received his master degree in particle physics from the University of Pisa, and conducting his thesis within the mu2e experiment at Fermilab. Okay, I will pass the mic to you.
No, thank you, Andy, for the nice introduction and for having me here today. And thank you all for attending. So the work that I will present today is an instead graph-based virtual sensing on sparse and partial multivariate observations. This is a joint work in collaboration with Andrea Cini, Daniele Zambon, and Cesare Alippi from Università della Svizzera Italiana, and Vladimir Gusev, also from the University of Liverpool, as myself. So the main focus of our work is virtual sensing. In words, this consists of using the available spatiotemporal measurements from real physical sensors to predict the whole signal at new unmonitored locations. In particular, we tackle a problem that current methods struggle to deal with. The task of virtual sensing from sparse sensors, which are far apart in space from each other. This is actually a common scenario. It is in fact common not to be able to densely cover large domains, and the reason can be multiple, like high measurement costs or ecological reasons or invasive sensing, like on human organs, for example. And while deepening this setting, we shall see how this is only solvable when covariates correlated with the target are available, which is the multivariate case. So I would like to start by presenting just an overview of the paper, a quick overview. So in short, we tackle the problem of virtual sensing with sparsely located sensors in space. I will first define the setting and show how the univariate formulation fails, which will then lead to our focus on multivariate virtual sensing. I will then present how we propose to solve the multivariate virtual sensing problem. And this will focus on what are the important dependencies that we need to take into account and model. And we will use a nested graph representation in order to model all of them explicitly. And with this methodology in mind, I will then present the architecture, which simply implements the framework by propagating information on such nested graph. And I will conclude with some empirical results. So we can start. So for starters, let's define our task and motivate our focus on the multivariate setting. So we start from spatiotemporal data. These are commonly defined as a collection of multivariate time series coming from distinct spatial location, usually identified by spatial coordinates in a generic domain, omega, which, for example, it can be the geographical space, like the one induced by the geographical coordinates, like latitude and longitude. And in each sampled location, we have our D channels that track the evolution in time of the different variables, as you see them here. And we use these orange strips to depict time series, and time flows from left to right. Now, if all data are aligned and synchronous across locations and across channels, it makes sense to represent data as a 3D tensor. So it's a n times t times d tensor, where n is the number of locations, t is the number of timestamps for which we record our signal, and d is the number of channels, so the number of variables. So these are the data. And now let's reduce ourselves to the univariate case. So only one time series is available at each location. So d equals 1. Imagine now that for some location of interest, there is actually no data, and our time series is missing entirely, and we want to predict that. We want to recover that. We can define a sensor availability mask, which defines if the sensor is available 1 or missing 0. And given this and the available data elsewhere, the virtual sensing task consists in approximating the probability of the missing time series given the spatial placement, so the coordinates of that location and the available data elsewhere. If we imagine a dense scenario where distance between sensors is small, basically, sensors will be spatially correlated with each other. And we can expect nearby sensors to have, to behave similarly. In fact, like missing sensors can be reconstructed by interpolating observations at neighboring locations. And this is what current methods do, either by simple interpolation or some more sophisticated deep learning techniques, but the principle stays the same. It's still an interpolation between neighboring observations. If we instead move to the sparse case, we see how it is not clear how to aggregate information from distant sensors, as basically the spatial correlation is lost. So either we have some strong assumptions on omega, or there are no relevant information to condition the reconstruction on. It is not clear how looking at your neighbor and at your first neighbors will help you, because they can be very far and much can be happening between your target and your available data. But this is a setting we want to solve. It is still important to be able to solve those kind of problems. And instead, let's now move to the multivariate case. We here first define a channel availability mask this time, which means that individual channels can be missing in our multivariate time series. In particular, if channel D is missing at location N, we will have a 0 in our availability mask. And the problem stays the same, reconstructing the missing time series from the observation data and the position. So the reason why this the multivariate case makes the problem solvable is that we now have information to condition on. In fact, the variables other than the target, which we name covariates here, provide some sort of partial observability and at our location of interest. And we can model the mutual dependencies between target and the covariates from the available data elsewhere. We may have both the target and the covariate elsewhere. And we can exploit this mutual dependency at the target location to impute the target given the covariates. There is also a second ingredient that contributes to solving this problem. So before, in the univariate case, we defined sensor correlation and similarity by looking at the proximity in space and the geographical coordinates, and that was fine. But now that coordinates do not convey much information on spatial similarity, we can still define it in a data-driven fashion. And even if channels are missing at some locations, a degree of similarity between distant location can still be learned from the other available data. It would be a similarity between location defining a sort of a latent space, if you know what I mean. Like while 2 points can be distant in space, they can be close in this latent space. Like regions can be very far apart on the globe, but have a pretty similar climates. And once we have this similarity, we can reconstruct our target by conditioning on the neighbors in this latent space. So this task of like a multivariate virtual sensing, it may seem a bit artificial at first, but it is actually important and common in many scenarios. So we provide here some examples of target covariates examples. So first example, let's say you want to predict and you want to know your renewable energy production on the entire globe. What you would do is that what you can do is that you can probably sample it only at a few representative locations, representative of some specific climatic conditions. And if you want to know your, for example, photovoltaic output in a different location, what you can do is that you can gather data from satellite climatic observations. Those are dense over the entire globe. You can superpose dense climatic data where you have sampled your photovoltaic data, but you also have them at your target location where you are missing the photovoltaic data. And you can infer that photovoltaic data from the dense climate satellite data. A very similar situation happens with material performance prediction or like degradation. If you want to know the degradation of a material based on the climate, you can expose your climate at your material at a few representative locations, but you cannot do it very densely because it's very costly. So you take a few measurements, and then you can use climate to then extrapolate your predictions elsewhere on the globe. Another examples can be like sensor networks where a channel may be failing, and you want to reconstruct them based on the remaining ones, or maybe a very expensive measurement that you can't perform everywhere. You can perform cheaper measurements, and then from them reconstruct your expensive variable where you need it. So this basically covers the setting. In short, we want to solve this task here in the figure. From such structured spatiotemporal multivariate data, we want to reconstruct missing channels at a particular location in the most optimal way, basically. So are there any questions regarding the setting or the motivations behind it before moving forward?
So basically, it's a data imputation problem.
Basically, it's a data imputation problem where you do not have the past history.
I see. Okay, that makes sense.
Exactly. So in some, it is a quite more challenging problem than pure data imputation. Yes.
Right. And then the like just in the example, so you're only like missing one of the rows in the red one. Could you miss all the 4 rows? So you have 0 information, but you're kind of doing like you have some node features, but you don't have any data on this node, for example. And then
so if you happen to miss all the channels, you are basically in the same scenario as the univariate one, that you basically have nothing to condition on. Yeah, you may have some scalar node features, but we do not consider them here. It's basically in the general setting. If you have no information at your target location and you cannot exploit spatial proximity, then the problem is basically ill-posed. You cannot solve the problem.
I see. That makes sense. Thanks.
Thank you. So if there are no more questions, I would move to the methodology section. Here we will deepen our proposed approach to tackle this problem and how we use a graph-based framework. So first of all, this is a key slide as it explains the 2 important dependencies that we use to solve the multivariate virtual sensing task. So here in the left side picture, I have depicted different multivariate time series. each group of time series, each vertical group, correspond to the same channels sampled at different locations. The multivariate time series on the right is the one where we consider having our missing channel, here highlighted in red, and this will be our reconstruction target. The other elements that we have at our disposal are the same channel, so the same variable as the target, but sampled at other locations, here indicated in this light green color. The available channels at the target locations, here highlighted in pink. And these are what we name the covariates at the target location. And finally, we have all the covariate channels at all the other locations that here are in yellow. So when inferring the missing channel, the first thing that we can look at are the green ones, the same variable observed elsewhere. So if some metric exists that can tell us how similar two locations are, we can identify the most similar to the target and then aggregate those locations to reconstruct our target. So we refer to these kind of dependencies between different locations as TY, which is from green to red. In other words, you model information flows across different locations, for each channel. And secondly, as I mentioned before, we can learn the dependencies between the target channel and the covariate channels from the available data, so elsewhere, and exploit them at the target location to infer the target channel in red from the covariates in pink. So we refer to those as CY, again, pink, red. And in other words, is basically information flow across channels within each location. So here vertically, basically. So now note that even if the yellow covariates are not used at inference, they are still key to training any model to learn both dependencies, as like we need them to unravel the dependencies between target and covariate to use them at the target location, but we also need them to define our similarity metric. So yeah, they are important. We can now proceed to the nested graph representation. So with those two important dependencies, so between locations and between channels in mind, we can move to the nested graph representation. In order to explicitly model both these two dependencies, that's what we use. We represent our data with a nested graph. So one graph connects locations and another graph connects variable within each location. In particular, we associate each location to a node of a graph that we call interlocation graph with the letter uppercase G. And since these model dependencies between locations, these allow us to model the TY relations. Secondly, we associate each variable within each bigger node to a node of a smaller graph, which we call intralocation graph, lowercase g, which allow us to model dependencies between variables, between channels within each location. Note here that the intralocation graph is assumed to be the same at all locations. We basically assume that the dynamical system generating the data does not change when we move to a different location. And additionally, for simplicity, we assume both graphs to be invariant over time. Next, so in addition to this, we also fully exploit a recent technique developed in this reference papers, the node embeddings. So these are free learnable vectors of parameters, and each vector is associated with a specific node of a graph. In our nested graph framework, this translates to associating a learnable vector to each node in the inter and in the intra-location graphs, which means one vector for each location and one for each variable, basically, in our pool. So n plus d embeddings. Note that the variable embeddings, the variable node embeddings are the same across locations as the variables they represent are the same. And so in the absence of coordinates, as we have said, they are kind of uninformative in this setting, we use in our work the capital G node embeddings to identify locations. And this proved to be very helpful. It's kind of a learned coordinates. The node embeddings are also very important, as shown in this paper, as they can account for better conditioning on specifics of individual nodes when performing some kind of global operations. For example, when we exchange information across nodes, across locations with shared parameters, the location node embeddings would provide the model with location-specific information that can help to kind of specialize the reconstruction locally. And we do this for both the bigger graph and the smaller graph to like specialize individual locations and individual variables. Finally, I have not mentioned how to get the adjacency matrix for the two graphs, but there are different design choices that can be made. They can be known a priori for some reason, depending on the spatial and variable domains, or they can be learned from the data. In this latter case, one can use some available and also quite sophisticated graph learning techniques or some simple strategies. For our papers, since like learning the best possible graph, it was not our main focus, we opted for simplicity and we built an adjacency matrix for uppercase G, so the bigger graph between locations, by using a similarity score between location node embeddings. And for the lowercase g, we just use a matrix of free learnable parameters. So both are fully connected graphs. This concludes the methodology section. So if are there any questions on this before moving to the architecture? Because if this is clear, like if it is clear what dependencies we want to model, so ty and cy, and like how we represent our data to allow for the information flow, then the rest will be quite straightforward.
Yeah, so there's a question from Ivan says, can you repeat how you build a smaller graph?
Oh, yes, the adjacency matrix for the smaller graph?
Yes,
I believe so, yeah. So basically is a matrix of free learnable parameters. Is like if you have d variables, that would be a d times d matrix of free torch parameters. I mean, a function of that. There is a softmax operation over that to kind of normalize across variables.
Why is it d times d? I'm still a little bit so
because it is d times d because it's the matrix between our variables.
okay,
the matrix
so there's a similarity matrix. Okay.
Is a adjacency matrix, yes, treated as a similarity matrix, yes, okay, to perform what will be the convolution of operations afterwards.
Okay, great. I have one or two like quick question. So
yeah, sure.
First of all, just conceptually, so here your setting assumes like is it required that at least one location must have all the node with the observed channels? Like, can you have like 4 locations and then each one is missing a different channel? Can this still work? But they are missing different channels, of course.
Yes, in principle you can. The model works just fine. You can right. Yeah, I believe it does.
Okay, sounds good. Yeah, and then so this looks like a hierarchical graph to me, basically enforcing that each subgraph or subcluster you are dealing with is the same. Um, what if there are some small variations in the graph? So I guess you talk about that for simplicity, that you can assume them to be the same, but like what if one of the sensor is a newer model and has one additional node attached to it, for example, uh, in this location? Um,
You mean one of the additional variable? If I have one additional variable for that,
yes.
we do not take that into account. That it can be seen as a limitation of this. Of course, you can like add one additional channel to all the others,
Right.
and have them empty. Have them empty, and the model will process that just fine. That this additional information would not be very helpful for the model. It will help to discard that pretty quickly.
I see. Okay, thanks.
So if there are no more questions, we will now have a quick view on the architecture. And yeah, so it is quite simple. In input, we have our data X, the availability mask telling us which sensors, which channels are available or not, and the node embeddings E for both the outer graph and the inner graph. As a first step, we encode our data and obtain a hidden representation for each data at each timestamps, location, and channel. This basically maps scalar points to vectors of dimensionality h. And next we update our representations by simply propagating the information over time and the nested graph, so locations and variables, just by means of convolutions over all those axes. Finally, we decode the representations by using the different MLPs, one for each variable, basically to account for differences in the channels, like different measurement units, for example. So this is in words. We can have a look at the equations here. I will show here all the formulas that contribute to creating our architecture without going into the details. Of course, it is worth just noticing that the encoder is actually a masked encoder, which means that it can create a representation even for data that are unavailable. This is particularly important for our task, as we want to reconstruct channels that are entirely missing. So we will have no data there in principle. And for those, the encoding is done by processing the node embeddings. You can see that for m equal 0, so missing channel, these terms, so the first term cancels out. And what remains is the processing of the node embeddings pair for the specific variable, so ed, and the specific location, en. We then recognize the convolution operations over time, so temporal convolution, and the two graph convolutions over the two kind of levels of the nested graphs, so interlocation graphs and intralocation graphs. And these three can be iterated to form some deeper architectures. Finally, we just have the channel specific readout, which I've mentioned before. And this is the whole architecture, basically, which we call graph-graph network. To evaluate the performance of the reconstruction model, we use the masked loss, which basically evaluate a time series similarity metric between the reconstructed time series and the ground truth time series. The problem is that we do not have access to the ground truth when the data is unavailable, obviously. This is a scenario that is similar to the one found in all missing data imputation problems. And in a similar manner to how people like tackle this problem in those similar settings, we artificially generate some missing data and evaluate the reconstruction error on those artificially masked data. So in particular, we simulate a transductive setting. As you see here on the right, we use a channel-wise train evaluation split. This means that among all the available channels at all locations, so the n times d channels, the whole pool of channels, we divide them into train, validation, and test according to some proportions. And when training the model, we also mask an additional fraction of training channel. This is very important at random, and train the model to reconstruct them. This is simply by not showing them during the model forward pass. We do not show them to the model during the forward pass, but we consider them in the training loss computation. This is very important as it biases the training towards performing our virtual sensing task of interest. We have found this to be very efficient and effective. Finally, we also mask out an additional fraction of data points, just individual data points at random, and this enforces some robustness into the training, basically, but it's way less important than the previous one. So this concludes this section. And are there any questions before moving to experiments on the like architecture and model training?
So basically, you are masking out some of the training data and never see them during training, and you provide better performance with that?
So we don't show them during the forward pass, but we evaluate the training loss on that data.
So you backprop the model.
Exactly.
Okay, I see. Okay, got it.
And this is like, just to add a little comment on that. It is important because if you see here before, when I reconstruct a particular value at timestamp d, location n, and variable d, the model has access to that specific point. If it is available, the model will see that. So if we don't explicitly bias the training towards virtual sensing, this will most probably learn an identity function between the data that are seen. So it is important to bias toward that. An alternative approach would have been to like use an autoregressive model, but this is what we have decided to use here. We have tried with the autoregressive model. This performed way better. So that's because of our choice.
Thanks.
Just to, no, thanks you. So last section, we will go through our experimental evaluation of all models. So first, some quick words on the baselines. We first consider a simple K and N average, K and N interpolation, which average the geographical neighbors, the nearest geographical neighbors. And as for the most advanced baselines, we divide them into spatiotemporal models and multivariate time series imputation models. So among the first class, we consider green, which is a graph-based model for spatiotemporal data imputation, which can perform virtual sensing as well. It needs a graph, and for it, we use a Gaussian kernel over the geographical coordinates to build such graph. This model focuses on like deeply aggregating information from spatial neighbors, and it's very effective to model spatial relationships. In addition to that, we also consider a small modification of the green architecture by allowing the model to condition on observations at the same time step of the reconstruction target. This was removed originally in the original green implementation as a regularization bias, which was effective in the univariate setting green was proposed for, but it is actually very important for our task. We need our model to be able to see covariates at the same timestamp because they may convey much information on the variable we want on the variable we want to reconstruct. And in the so in the second group instead, we consider BRITS, a bidirectional RNN model designed for like generic multivariate time series imputation, and SAIDS, which is again a global imputation model, but relying on self-attention. And it's considered one of the state-of-the-art for multivariate time series imputation problems. So they both focus on the relations between different dimensions of the input multivariate time series. But in both, there is no notion of space, and like different locations are treated as independent and as different training instances in our framework. Basically, to train a global model with shared parameters across locations. We also, like on a note, we also compare to some more progressively advanced recurrent neural networks from a kind of progressive ablation study toward like considering first without just a one directional model, then a bidirectional model, and then we add the node embeddings, and then we add the graph. So basically gradually progressing towards our approach. As for the first experiment, we consider a very dense climatic data set from satellite data. From it, we sample a few climatic variables only in the correspondence with the 235 national capitals in the world. And we do this in order to provide a good degree of sparsity to recreate a sparse problem. While of course it can happen that a few capitals are close to each other, they are mostly well separated on the globe. Most of them are well separated. So we consider two different temporal resolutions, and we consider different climatic variables with a different degree of correlation. So while some variables will be highly correlated between each other, others will be not. So we hope to see this reflected in how accurately we can reconstruct them. And our task here for the climate experiments proceeds by simulating random missing channels in this 3D dataset. So random missing channels in random locations with proportions 10% validation, 20% test, and aim to reconstruct them. Basically, it is a missing channel at random task. And we show the results in this table. Here you can read the mean relative error in a channel-wise fashion, so column-wise. And basically for every variable, we average across all locations for which that variable is a test channel. So and uncertainties represent standard deviations across random seeds. We can notice a few things. First, like in short, our architecture outperforms all baseline pretty consistently across channels. Like by modeling both type of dependencies, while both do not do that explicitly, not both at least. Second, you can see that the reconstruction error is higher in correspondence of the variables that are much harder to reconstruct based on the other. Like precipitation, for example, is very hard to reconstruct based on the others, while temperature is quite easy because you have highly correlated covariates, like one of the others is temperature max or temperature range. And so like with them, you can easily reconstruct temperature mean and probably vice versa. Also note that the most important column where we average all results, so across locations and variables, like you can see how the improvement is pretty significant. And the same goes for the harder hourly experiment, the hourly resolution task. As a second task, we focus on reconstructing a specific variable So given some covariates that are always available, so in order to prepare this experiment, we start from a very dense data set of simulated photovoltaic output over the United States. And from it, we sample the signal just over a very few random locations. Then, at the same locations where we sampled photovoltaic data, we also sampled climatic data from the same satellite data set as before, the dense satellite data set as before. So what we end up is a data set with one photovoltaic channel and 10 climatic data. We split 70% of the photovoltaic channels and we consider them as train channels, 10% as validation, 20% of our test, while we assume climatic channels to be always available at train. So our aim here is to reproduce a scenario where one wants to predict photovoltaic output at a new location, while having climatic data available everywhere was one of the motivations we mentioned at the beginning. Here we show in the table the MAE for the test photovoltaic channel, so watt per hours. We can appreciate how the improvement of our model with respect to the baselines is more pronounced as more locations we take into account, which we believe it can be related to a better handling of spatial relationships, even in sparse scenarios. And to conclude, in the paper, you can also find a few additional qualitative results, which, they contribute to the discussion. In particular, I would like to highlight our TSNE visualization of the learned node embeddings, the learned location node embeddings, so uppercase G. So here we have one embedding per each climatic, per each capital. So this refers to the first experiment. And we have superposed climatic labels corresponding to the Köppen-Geiger classification of climates according to some rules. And for each capital. And note that the alignment between the format clusters and the labels is pretty strong. And also recall that the model has never had access to either the geographical coordinates of those capitals nor such labels. And this demonstrates the ability of the model to capture similarity in the latent climatic space. I will not go through the more analysis, but you can find them in the paper if you are interested, but there are quite a few of them, like for example the ablation study on the importance of the temporal location and variable convolutions. I would just like to conclude by mentioning a few future directions. In terms of performance, it would be, of course, beneficial to specify the operations instead of using fully connected graphs and consider some more advanced graph operations, for example. Also, it would be interesting to extend the model to be inductive because in the current state, the model needs the training of the node embeddings for every new location that is added to the dataset or that someone wants to make predictions at. Yes, and lastly, this work kind of goes in the direction of performing virtual sensing in general domains, as there is no notion of a geographical space in our model. The position of each location is learned jointly with the network weights by using the node embeddings, and we use no coordinates at all. So it goes into that direction. For example, a space of medical patients where multiple time series are collected for each patient, and one would like, for example, to reconstruct missing exams for specific patients. However, this is quite of a challenge because it is not clear to what extent different patients influence each other at inference time in particular, and how to handle the asynchronicity between different patients. but it will be a very interesting direction. So this concludes my presentation, and from all the team, I thank you all for your attention. Please reach out if you have any consideration or feedback. And yeah, we are now happy to take any questions, and thank you again.
Yes. Thank you for the great presentation and very nice description of the problem and your architecture and so on. And if there's any question from the audience, please type in the chat, and I will I can ask them now, or you can just like unmute yourself and ask yourself. So do you think we can derive some theoretical bounds for how well you can reconstruct the missing data? So for example, if you go back to the healthcare like setting that you were talking about, so potential future direction, of course you want to have a notion about how bad your prediction could be if we are to use it in like critical scenario, right? So how do we know it's not going to default into a general profile of patients, like just kind of merging all patients into a mean and then like predicting from that, and then instead of like learning a like personalized prediction, can we say something about how well models can reconstruct the signals in the missing channel so that it's bounded in a given range with some assumptions?
Yeah, there is. This is a kind of a thing we are exploring actually right now. Is like pairing a model like this with an estimation of the uncertainty, and like giving a kind of a bound, and exploring exactly how far. I mean, when you are far from your training data, you will always have some big uncertainty. In the case of like in general domains, it is definitely trickier than in geographical domains, because there the notion of time is more straightforward. So like if we want to like proceed step by step, I would say that the first step is to correctly quantify uncertainties and like confidence in the like spatiotemporal setting, in the multivariate spatiotemporal settings. So how well knowing the covariate in your new location will help you reconstruct that specific target that's not known at the moment, and we are working on deriving bounds for that. And after that, it will be interesting to move to general domains. Yeah, but I would say only after that. Only after handling the ordinary spatial problem first. But yeah, definitely something to work on. Also, I'm focusing on, as you mentioned that in your kind of introduction, on material performance. And it is not that you only expose one material to different climates, but you have many materials. So you also want to model not only how a single material behaves in different locations, but you also want to model dependencies between materials, so chemistry basically. Dependencies between how different materials perform. And that's a kind of a similar challenge of general domains like patients. Very similar.
Right, that makes sense. Yeah, so thanks for the great answer, and looking forward to your future work once that came out. That sounds very interesting. I think like in general, knowing the uncertainty about like temporal predictions is a very important direction. So we have a non-technical question from Donna, and she also thinks your presentation is very nice and clear. So she asks, how do you design your images? So what kind of graphical tools do you use?
Yeah, I use draw.io. Draw.io. Kudos to the guys at the Università della Svizzera Italiana for pointing me to that.
Okay, nice. Great. Okay, sounds good. If there's no more questions from the audience, we can wrap up for today. And let's thank the speaker again for the great presentation. And yeah, so I will see you at the future reading group.
Yeah, thank you all.
Thank you. Thanks. Bye.